Now that we know so much about the series and how to determine whether they converge or diverge, let's produce the summary of everything that we have learned so far. So, the procedure of determining whether a series converges or diverges can be summarized in the following way. So, given a series with all positive terms, the question is, does this series converge or diverge? And we usually start the process by trying to recognize one of the well-known series. So there are three of them: geometric, telescoping, and the p-series. And the reason we want to do that is because these are the easiest ones to deal with. So the geometric series looks like this, the p-series looks like this, and the telescoping series, there is no way to describe what a telescoping series looks like. But the idea is that when you write out all the terms, you're going to have some, telescoping, like some cancellation going on, and your series kind of collapses to something that's more comprehensible. And the test for geometric series is very simple. You look at the common ratio, and if it is greater than or equal to 1, then the series diverges, and if the common ratio is less than 1, then the series converges. Don't get mixed up with the test for p-series, because it's actually somewhat the opposite. If the p value in a p-series test is greater than 1, then the test converges, and if it is less than or equal to 1, then the test diverges. And what's nice about geometric series is that we not only know that it converges, we also know what it converges to. It's going to converge to the first term divided by 1 minus r. Now, the telescoping series is a little different, so again, it's really hard to summarize all possible behaviors there, but the idea is that instead of looking at the series, we're going to be looking at the partial sum and at the limit, and if that limit does not exist, then the original series diverges, and if that limit does exist, then the original series converges to that exact limit. So the geometric series and the telescoping series are the only series for which we can easily find what they converge to. So keep that in mind. So if the problem says find the limit, most likely you have either a geometric or telescoping series. Now, if you haven't recognized any of these three patterns, then you should set up and perform the divergence test. Basically, find the limit of the nth term, and if that limit is not equal to 0, then the original series diverges. If that's not the case, so if that limit is equal to 0, or you cannot find it, then proceed to the next step. And the next step is it involves running one of the convergence tests one after another, and you do that until you get the test that actually cracks the case. So we altogether learned, we're going to list here 5 different tests, and each test, you don't just randomly apply tests. Usually you try to recognize some sort of hint or pattern, and let's summarize that over here. So the first test that we learned was the integral test, and you only do integral test when, well, first of all, there are a couple of conditions that have to be satisfied, but most importantly, you better have some easy integral after you set it up. If that integral is not easy, then don't even bother setting up the integral test. Another test we learned was the direct comparison test. In the direct comparison test, we exploit some inequalities and we established some bounds for the given series, either below or above. And here are some of the common inequalities that are used to recognize the direct comparison, the problem that is good for direct comparison. Again, direct comparison is not the best test, and we have seen examples before when it doesn't work, but the limit comparison test does work. So in the limit comparison test, we basically want to identify a series that is compatible with some other series, which we definitely know whether it converges or diverges. So in the limit comparison test, we're looking for a series that I call like P-like series or G or geometric-like series. So they're not quite geometric, but they do look like geometric. So for example, this is not geometric, but it totally looks like geometric. This is not a P-series, but it totally looks like P-series. So these were some examples for which I would set up the limit comparison test. Then we have two tests that are actually stronger. They are testing for the absolute convergence. So we have the ratio test and the root test. But we know that the absolute convergence implies the regular convergence. Now, when do we use the ratio test? If your problem has a factorial, you probably want to try the ratio test. It should be one of your first thoughts. And we definitely use root test when we have something like raised to the nth power as the general term of the series, of the given series. So these are again just the hints. It's not guaranteed that whatever test you picked will work, but you are definitely better off when you have a plan. And this summary is a good solid approach to any problem. Now we deviate a little when we have an alternating series given to us. Usually when an alternating series is given, the question, while remains almost the same, so we want to know whether it converges or diverges, we also want to know whether it converges absolutely or conditionally. So there are two types of convergence, and for regular series that in which all the terms are positive, it doesn't matter, but for alternating series, it does matter. So when you have an alternating series, you immediately set up the alternating series test, which we abbreviate AST, and you set it up easily by, it's almost the same way as the divergence test. You just basically try to find the limit. Now, if the limit is equal to 0, that's the question, right? So if, I guess the easiest case, if the limit is not equal to 0. So if the limit is not equal to 0, so the answer is no here, then the result is diverges, and it diverges by the divergence test. Now, if the limit is equal to 0, so if you answered yes to this question, then you still have to check a couple other conditions, and one of them, well, here both of them, your sequence must be positive, and it must be decreasing. I guess, yeah. So if in addition to the limit being equal to 0, two of these conditions are satisfied, then the conclusion is that the alternating series converges, and the reason why it converges is the alternating series test. That's the conclusion. And in this case, so if you determine that the series converges, we now need to determine whether it converges absolutely or conditionally. And to answer the next question, whether it converges absolutely or conditionally, we're going to ask whether the series made of just the terms without the alternating factor, whether that series converges or diverges. Now you may ask, like, well, how do we do this? Well, remember, we have a perfect plan for tackling exactly this task. So once you take the absolute value of or once you drop the alternating term, you just have a regular series, and then you can run through this process to determine whether it converges or diverges. And if it converges, then the original series, the original alternating series, is said to converge absolutely. And if this series diverges, then the original alternating series is said to converge conditionally. So this is our plan, and I guess the worst case scenario is when you can't find this limit for whatever reason, so you're not sure how to answer this question. In such a case, I guess you can jump straight to ratio and root test. Hopefully that will answer the question, but again, this worst case scenario can continue. What if those are inconclusive? Well, that's really the worst case scenario, which will require something that's beyond this class. Anyway, so this is the summary of the everything that we've learned. So let's apply what we've learned and try to do some examples. So the first thing we're going to do here is this geometric? No. Is this telescoping? I don't know, but by now you guys should know some of the common telescoping series, so it doesn't look like it. But if nothing else works, maybe we can come back here and investigate this. Does it look like P series? Also no. Let's set up the divergence test. The limit 2 to the power n over n factorial, n goes to infinity. We cannot use that useful theorem here and turn it into a continuous function, because factorial is not a continuous operation on real numbers. And but there are other ways to convince ourselves that this limit is equal to 0, which makes the test inconclusive. Now we're gonna pick one of the convergence tests, and which one are we going to pick? Let's take a look at this summary again, and again, we're not going to be able to integrate it because the function is not continuous. Direct comparison test here, probably not a good idea. Limit comparison, no. So again, I recognize the factorial, so I'm going to go for the ratio test here. So in the ratio test, we're going to set up the limit as n goes to infinity of the nth term in the denominator, n plus 1 term in the numerator. Now everything is positive, so we don't need the absolute value. Let's write it as a single fraction. The numerator and denominator have a lot in common, so 2 to the power n plus 1 can be written like this. N plus 1 factorial can be written like this. And now we can cancel all the things they have in common. And as n goes to infinity, this limit is equal to 0, which is less than 1. That means the original series converges by the root test, a ratio test. All right, let's continue. Let's do another example. In the next example, I'm going to change the task a little bit. So let's say we have the following series. And the question says, instead of standard determine whether it converges or diverges, it says, in addition to that, it says, if converges, find the limit. Now we know that there are only two types of series for which we can find the limit. So we're gonna use this as a hint. And the hint is that it is either geometric or telescoping. And we're gonna spend quite some time is actually in step 1 trying to figure out whether it's geometric or telescoping. And it does not look like geometric, so it's gotta be telescoping then, right? So to telescope it, we're going to use the partial fraction decomposition, and we can rewrite this in the following way. You can easily check that this is true by finding the common denominator and like subtracting things just to verify. But again, this was the hardest part, actually noticing this. Now we're going to express the partial sum, the nth partial sum. So we're going to have 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, etc. until we get to plus 1 over n minus 1 minus n, and so on. Sorry, there's no so on. This is the nth partial sum. And now what do we notice here? That 1/2 is cancelled. This is what I call telescoping, right? So everything telescopes and your entire expression collapses, or the entire series collapses to this. So this is your nth partial sum. Now we just find the limit of the nth partial sum, and the limit is clearly 1. So the answer, this converges to 1. Why? How? Because it's a telescoping series. So we found we determined not only that this converges, but also that it converges to 1. All right, let's do another example. This looks interesting. So the first question, is this geometric? Doesn't look like it. Is it telescoping? Doesn't look like it. Is it p-series? Doesn't look like it. Let's set up the divergence test. Hopefully it diverges. And the limit of the nth term, and this limit is not trivial, right? So we have 1 to the power infinity, and I'm actually not sure. We don't want to say it diverges here, right? Well, we do want to say it, but is it really true? Because 1 to the infinity can be actually 0. So we don't really know what this is, and instead of committing ourselves to spending the next 10-15 minutes trying to find this limit, let's do something else. Let's try to apply one of the convergence tests, see if it works. Let's go back to our plan over here, and it does look like we can try the root test. So in the root test, we set up the limit of the nth root of the absolute value of the nth term, but since everything is positive, I'm not going to write the absolute value. But recall that nth root is the same as raising to the power 1 over n. So what we have here is actually n over n plus 1 to the power n squared, and all that to the power 1 over n, which, if you use the properties of exponents, can be simplified to n over n plus 1 to the power n. Now we can use the very useful theorem and look instead at this function, which is continuous. And let's see, this pattern is recognizable, and I kind of want to leave it up to you to find this limit, but the hint is, we've done this earlier, if you call this limit L, then ln of L, I guess we can just do it, ln of L will be x times the ln of x over x plus 1, and this then can be rewritten as ln of x over x plus 1 over 1 over x, and then we can use the L'Hopital's rule, so it's going to be -1 over x squared, and in the numerator we're going to have the reciprocal of that, so 1 over x, so it's going to be x plus 1 over x times the running out of space here, times the derivative of what's inside of ln, which we use the quotient rule, so numerator, derivative of the numerator is 1 times x plus 1 minus x divided by x plus 1 squared. And if we reduce everything here, if we simplify, so x is gone, this x plus 1, this square is gone, this x and this square is gone, and we basically have negative x over x plus 1. So that limit is equal to -1. But remember, this is just ln of L. L will be e to the -1. Why? Because ln of L is equal to that. And what does that mean? Well, luckily, I guess once again, I'm going to move things around. This 1 to the power -1 is 1 over e, which is definitely less than 1, and that means that this series converges by the root test. Again, there are infinitely many problems. What's more important here is for you to develop a systematic approach to try to answer the question about the convergence of a given series. So this was the summary of testing procedures for determining the convergence or divergence of a given series.